We are discussing now the pulse position modulation. In the pulse position modulation, the pulse position is varied according to the modulating signal amplitude. Now how it done in the experiment, that we'll see. Now here, this is what the kit for the pulse position modulation, and for the pulse position modulation, the frequency, that is the modulating frequency I have used, that is 1 kilohertz. It is given to the pulse position modulation. This input is given, and this is what the output of the pulse position modulation. Output of pulse position modulation is given to the buffer. Here we are using this buffer circuit, and from the buffer it is you can see the output. I will check output here at the buffer. Now the demodulation is done here, so it is given to the demodulation section. So I have given it to the pulse position demodulation. The switch is kept at pulse position modulation. You can, if you will put it here, so it will be the pulse width modulation. So we are doing now pulse position modulation. Then this modulated output is given to the fourth order Butterworth filter. So this filter will give us a smooth output. So we will check here the output. Now I'll explain you, I'll show you the one by one. So this is what the input of 1 kilohertz, and the clock is there. So for the clock we have option, that is 8 kilohertz and 16 kilohertz. So we are using 16 kilohertz because this jacket is kept at the down. So this jumper is at the down. So this is 16 kilohertz we are using, and we are taking the output. I'll just show you at the CRO. Here I have captured. So this is what your input modulating signal. So this is what the signal, we can see the parameter of the signal. So input signal, I'll note it down. What is the frequency? So for the yellow one, the frequency is 957. Okay, so you can note it down, the frequency 957.5 hertz. So it is around 1K. So this is what your input. Then the clock frequency, you can see the blue one. So the clock is comparatively high, and you can see the clock frequency around 16. So it is 15.36 kilohertz. So it is 15.36 kilohertz. Okay. So this input signal and clock is shown to you. Now we will see with reference to the clock the modulation. Now unlike other modulation, here the pulse position is varied. So pulse position we cannot check according to the input, because this is the sinusoidal. So we cannot have, so we should have the reference. So with reference to the clock, I'll check. So I'll keep clock as it is, and whatever the input, now this input is taken here. So instead of this input, so I'll take the output. So I'm getting output here. So this output I am connecting to the CRO. Okay. So this is connected. I will check that how the I'll do the auto set. So again it is doing the automatic setting. Now I'll just adjust the position so that we can compare. Okay. So here I have taken the pulse position. Now the pulse we are looking like the same, but if we will compare it, so we can just check that what will be the pulse position, and I'll just do the enlarge so that we can take the reading. So I'll taking reading from the start. So here I have a facility, so I can start. So you just see every rising pulse, this is what the clock, and this is what the pulse position. So I'll take with reference this blue one. Blue is the clock, and the blue yellow is the pulse. So with reference to this blue, I am taking the pulse position. So I'll just move it here at one reference so that I can do the reading. So yes, okay, so you can just check. I'll just So I hope these dots are visible. So each dot, so this is blue is the 0 reference I am taking. Now I am measuring the time period. So this is blue dot, that is 0.2, this 0.2, and this is 0.2. So 0.2, 0.4 and 0.6. So I am getting here a phase shift of 0.6. Okay. So my clock reference position is 0. I am noting it down 0. And the position of the pulse, that is at 0.6, okay, at the right hand side. Multiplier, you can see that is the 10 microsecond. So for your reference, the multiplier is 10 microsecond. So you can convert it into the time. So it is expected. I'll keep it for you. So simply if you will multiply by 10 microsecond, so the time period that will be considered here. So this is 0.6. I'll go for the next position. Now again for the next position, this is what horizontal yellow, blue, and this is yellow position. So yellow is at the, you can see 0.2. So 0 is taken as a reference and the 0.2. You can multiply by 10 microsecond afterwards. So it will be 60 microsecond, 20 microsecond, that way. So I am taking simply the reading so that we can verify. I'll go for the next pulse. Now you just check, this pulse is towards right, this pulse is towards right, now this pulse is towards left. So if this pulse reading I am taking plus, this is also plus towards right side. Now this pulse is shifted towards the left side of this yellow line, that is the rising clock. So I am taking this as the negative. So I will take at the reference. So it is at the left hand side of the pulse. So accordingly I will take. So again it is 0.2. So this 0.2 I am taking as minus 0.2. So 0. So this way. So it has changed the position. Now again I will go for the next pulse. So let's see what is the position for that. I am taking this as a reference to 0, blue one. So it is 0.2, 0.4, 0.6. So again this is 0.6. So minus 0.6. Reference is I am taking 0. Then I will go for the next position. Again you can see, again I will take the pulse at the 0, and this is 1, and again it is 1.2. So minus 1 point, you can see the complete 1 and it is here. So 1.2 I can take, reference is again 0. Then I will go for the probably the last pulse. Okay, so this is the pulse here, line, and here. So it is 1, 1.2, 1.4 and 1.6. So it is minus 1.6. Reference is 0. Now you just check on the observation table, that is 0.6, 0.2 plus minus 2, 0.6 minus 1.2 minus 1.6. So there is pulse position variation with reference to the clock. The variation is there. So as the voltage increases or decreases, the variation is there. Either the pulse is shifting towards left or right of the clock. Okay. So this variation we can see here also. You can see it is, this pulse is at the left. Sorry. This pulse is at the left, then this pulse is also at the left, this pulse is at the left, so all are negative. This is also at the left, again negative, and this pulse is right to the rise, so this is positive, and this pulse is at the right. So 2 positive reading and the remaining 6 are the negative reading. So by this you can see the variation is there. And time period, if I am to put the another column, so I'll have a multiplier as 10 microseconds. So I'll just put here the reading so that you will get in terms of the time. So time difference, so here pulse position time with respect to time, same, the pulse position you can see. So it is division and it is time. So for the pulse position, So multiplier is 10. So it is 6 microsecond. It is 2 microsecond. Again minus 2 microsecond. Again minus 6 microsecond. Again minus 12 microsecond and minus 16. So this minus sign is for the position. Time is not minus. So minus sign is only for the position, so that we can indicate the position, because this is 2 and 2. So if you will consider both has plus 2, so they are on the same position, but they are not. The difference between this is 4. Okay, 4 microsecond. Here the difference again 4 microsecond. Here the difference 4 microsecond. Here 6 microsecond. Again 4 microsecond. So 4 to 6 microsecond difference is there in the position. So accordingly it is varied. So this we can prove it from this table, or the variation is there with reference to the clock. So this is what the modulation is done, and we have proved here by the experimentation that how the pulse is moving, it is varying, and how the position is varying. In terms of the times also we have considered. Now we will go for the demodulation. Now for the demodulation we have to take the input reference. So what I'll do, so instead of this clock, I'll take the reference as input. So one of the input here, so this is what I'll take this as the clock. So this is 1 kilohertz. I'm taking it to one channel, and for the another channel, okay, I'll take the output. So I'll take the output for the another channel. So we can just do the auto save. I'll do the auto save. Okay, so here I'm getting this two pulse. Okay, so one is input and another is the output. So here the channel 1, here the channel 1 is the input. You can see this channel 1 is the input, and channel 2, that is blue one, is the output. Now we can see the phase difference. I'll just align this so that we can see the phase difference. So input I have taken as a reference. So I'll just address the input. So input I have taken as a reference, and this is the blue one is the output. So we can take the phase difference. Okay, so the phase difference we can check. Okay, now I'll just take the reading for phase difference. Phase shift is equals to, now what is the phase shift I am getting here? This is my starting rising edge, and this is rising. This is what division 1, and this is 1.2. So my multiplier is 1.2 multiplied by time per scale. So my time multiplier is 250 microsecond. So I can go for the same, that is the 100 microsecond or 500 microsecond. So accordingly you can check. So here it is 250 microsecond, and the difference is 1.2 multiplied by 250 microsecond. This multiplication you can do, and I'll just take the total time period, so that the total time period, this is the phase shift, and time period T, total time period. So total time period of this is 1.043 millisecond. 1.043 millisecond. So with reference to this, this total, that is 1.2 into 250 microsecond, you just calculate how much is this. So this maybe I'll say the short small t. So small t by capital T into 360. So you will get the complete phase shift. So that I'll keep it for you to do the this by your own. So you can do this multiplication and do this. So this is what the pulse position modulation. In the pulse position modulation, we have experimentally proved here that how the pulse position is varied and here we are taken a reference as your pulse, your clock. 16 hertz clocks we are taken as a reference, and that with that reference how it is varied, because if we will take this sinusoidal signal as a reference, it is analog, we cannot have the variation, we cannot check it out, because as how it is increasing the voltage and accordingly the pulse position is increasing, so that we can check. But as we have the facility of 2-channel CRO, we cannot use the third one, that is the input signal. So that's why we have compared with the clock, that is 16 kilohertz, and the whatever the variation is there, that is the modulated output. So this is about the pulse position modulation. Thank you very much.